Alright, well, welcome. I'm going to just try and do a few review problems today. I wish you were here to be able to ask me questions. But I just want to try and get you familiar with some of the kind of things that might be in the exam. I'll try and make most exam problems similar to these. So suppose I use the sum of the product identities to rewrite this expression as a sum of trigonometric functions and evaluate the result exactly. Well, I'm going to have to give you the identity with it. I said you don't, actually the whole thing is open book this time. But on these, I don't expect you to memorize the sum to product and the product to sum identities anyway. All the others I want you to memorize, but these are not used as often. So we'll say I can use this identity if I just call 105 degrees, if I want to evaluate cosine of 105 degrees plus cosine 15 degrees, and you're given the formula with the problem. I'll give you that if I give you this kind of problem. It says that cosine A plus cosine B, just reading right off of there, is equal to twice the cosine of A plus B over 2 times the cosine of A minus B over 2. So I just take this plus this over 2, 105 plus 15 over 2, and this one minus this one over 2, 105 minus 15 over 2 is twice the cosine of 60 degrees, cosine of 45 degrees. Those are special angles. I can do these exactly using the triangles, right? We remember this one. Well, let's see this version of it. 1/2 square root 3 over 2 and 1. The cosine is this one over this one is just 1/2. The cosine of 45 degrees. We draw that triangle 1 over square root 2, 1 over square root 2 and 1. Or you can write these as square root 2 over 2. This one over this one is 1 over square root 2. So this side times this side over this side gives us 1 over square root 2, and I'll wind up this with 1 over square root 2. Here's the next problem, number 2. If I want to take the tangent of minus 75 degrees, that's not a special angle. But if I notice that it's half of a special angle, I can evaluate it exactly now with the half angle identity. Look, it's exactly, first I'm going to do one thing first. Since tangent is odd, I can pull the minus out, right? This is minus the tangent of plus 75 degrees. You don't have to do that, but I find it convenient to get rid of the minus sign. Now 75 degrees is exactly half of a special angle, 150 degrees, so I'll apply the half angle identity. Tangent of 1/2 an angle is plus or minus the square root of 1 minus cosine of the angle over 1 plus cosine of the angle. Right? So if I just call this theta, tangent of theta over 2 is 1 plus or minus square root 1 minus cosine theta over 1 plus cosine theta. So this angle is double this one. Now, since 150 degrees is a special angle, I can evaluate it in the unit circle. I'll draw the 150 degree angle, drop a perpendicular, I get this 1/2 square root 3 over 2, 1 triangle. The cosine is the x-coordinate, evidently minus this distance, minus square root 3 over 2. So I get 1 minus a minus square root 3 over 2 over 1 plus a minus square root 3 over 2. And then I'll say, well, to figure out plus or minus, you don't look at the 150 degrees, you go back to the beginning. I'm calculating the tangent of this angle, which is minus 75 degrees. It's in quadrant 4. We know tangent is negative in that quadrant, so I'll put negative here. But you go to the original function, is it supposed to be positive or negative based on the quadrant of this angle? Use that one here. So I'll carry the minus now, and I have 1 minus a negative square root 3 over 2 over 1 plus negative square root 3 over 2, square rooted and minus. To get rid of the compound quotients, I have to simplify it as part of the problem. I'll multiply top and bottom by 2, the least common multiple of the denominators that I see. You get 2 plus square root 3 over 2 minus square root 3. And how do I simplify that? Whenever I see an a plus b square root c on the bottom, I multiply by its conjugate. So here's conjugate. So 2 minus square root 3 I multiply by 2 plus square root 3. I have to multiply on the top by the same so I don't change the quotient. So multiply top and bottom by the conjugate of the bottom. Now the bottom is 4 minus 3, if you FOIL it out, is 1. So the bottom just reduces square root 1 as 1. The top is a square root of a square, so it's just the quantity, 2 plus square root 3. And then there's a minus out in front of the whole thing. We wind up with minus 2 minus square root 3 for problem number 2. Alright, let's try number 4. Number 3 is very similar, just with a half angle identity instead of a double angle identity. You might try that and send me an email if you can't do it. On number 4 here, I'm asked to use the double angle identities. If secant x equals square root 5 over 2 and sine x is negative, find the sine of 2x. Remember that if you know one trig function and the sine of an unrelated one, plus or minus, then you can find all 6 trig functions. So I know I can find sine, cosine, tangent, cotangent, secant, and cosecant of x, all of those because of this information. Now if I'm asked to find sine of 2x, I know there's a double angle identity. Sine 2x is 2 sine x cosine x. So once I have all these trig functions, I can evaluate the sine of 2x. Same thing applies on the half angle identity. Given one of the trig functions, cosine, you can find all, and the sine is less than 0. You can find all 6 of them, then you can use the half angle identity to evaluate that one. Using the trig functions you found. Here's how you find the secant of the sine of 2x, given the secant is of x is square root 5 over 2. From the secant, you take its reciprocal to find the cosine, right? Secant is square root 5 over 2, cosine is 2 over square root 5. Once you have the cosine, you can find the sine by the Pythagorean identity, solve for sine. Sine is plus or minus square root 1 minus cosine squared. But we're told sine is negative, so we choose the negative sign. Well, 1 minus, this is 4/5 when you square it, is 1/5, so you got minus square root of a fifth, or minus 1 over square root of 5 for sine. Now you write down the double angle identity. Sine of 2x is 2 sine x cosine x, is twice the product of these two that you found, is minus 4/5. Alright, well, 5 is another, this is a product to sum identity, or product to difference. I'll let you work on that. It's sort of similar to the first one. Let's try number 6. Solve a trigonometric equation exactly on a given interval. I'll probably ask you one of these. Suppose we do the second one. The secant of 2 theta is minus the square root of 2. How can I solve that for all theta between 0 and 2 pi? Right, within one rotation. Well, if you're given secant or cosecant equal a number, well, actually, if you have a double angle in there, first thing you should do, if it's a 2 theta or a 3 theta, is reduce it. Make a substitution. Let u equals 2 theta, so now it's secant u equals minus square root 2 over 2, minus square root 2. Now, once you've done that, rewrite it as sine or cosine if you can. By taking the reciprocal here, secant of u is reciprocal is cosine u, and the reciprocal here is minus 1 over square root 2. I find this is equivalent to cosine u is minus 1 over square root 2. But cosine is the x-coordinate, so now I can solve on the unit circle. I find all points with x-coordinate minus 1 over square root 2 by plotting that vertical line, x equals minus 1 over square root 2. There's 2 points in the unit circle that can have the terminal ray to give those values. If I draw those terminal rays, I notice that it's 1 over square root 2 to the length on this side of the triangle, 1 on this side. It has to be a 45, 45, 90 triangle, and this one by symmetry also. So we have that u could be 3 pi over 4 or 5 pi over 4. But we're not going to be satisfied with finding just the ones within one rotation. Even though it said theta in one rotation, u being 2 theta, you actually have to let it be between 0 and 4 pi, or let's even easier, just find all of them and throw out the ones we don't want. So let's find all solutions when we made a substitution, and then throw out the ones that aren't in one rotation. So all solutions are 3 pi over 4 plus any multiple of 2 pi, right? We write 2k pi to indicate k rotations. We could go around once and come back here at k equals 1, or go around twice and come back here at k equals 2. This represents all ways of getting this terminal ray. This is all ways to get this terminal ray. So theta could be, or u could be these, but u is 2 theta, so dividing through by 2, theta can be half this, 3 pi over 8, plus half this, k pi. Or half this one, 5 pi over 8, plus half this one, k pi. Now we'll try plugging in different values of k and see which ones give us theta between 0 and 2 pi. When we plug in k equals 0, if 3/8 pi is true, k equals 1 gives us 11 pi over 8. That's less than 2 pi. That would be 16 pi over 8. Similarly, 5 pi over 8 with k equals 0, and 5 pi over 8 plus pi when k equals 1. All other values of k, if you put k equals 2, for instance, 2 pi plus something is bigger than 2 pi, it's too big. Put k equals minus 1, then you got something less than 0, it's too small. These are the only solutions, these 4. Well, here's a good one, 7b, pretty difficult. Another solve the equation. You'll get a solve the equation problem. Suppose this time I have a square in here and a first power of a trig function. These kind you need quadratic formula for, and the way you, or factoring, one or the other. The way you see that is you just let u equal secant theta. Given 2 secant squared theta minus 2 secant theta minus 3 equals 0, let u equal the trig function secant theta, and it becomes 2u squared minus 2u minus 3 equals 0, a quadratic equation. We know we can always solve a quadratic equation. Often we can solve it by factoring, but not so in this case. This is the unlucky case. For the test, you need to memorize the quadratic formula. U equals minus b plus or minus square root b squared minus 4ac all over 2a is the quadratic formula with a, b, and c, the coefficients of u squared, u, and the constant term. So by plugging these in, minus b is plus 2, right? B squared is 4, and here's minus 4ac all over 2a. I find out that u can be 2 plus or minus square root 28 over 4. If you were to factor, you would have had to factor with these numbers in, or you would probably never have got that. That was a terrible thing to try and guess how to factor. So this one required the quadratic formula. Well, we noticed that square root 28 is 2 square root 7, and so now we've got a common factor of 2 on the top and bottom. Let's factor out the 2, right? This can be written as 2 times 1 plus square root 7, right? Plus or minus over 4, and so dividing top and bottom by 2, I've got 1 plus or minus square root 7 over 2. That means if u is equal to 1 plus or minus square root 7 over 2, where u is secant theta, substitution, then cosine theta is its reciprocal, 2 over 1 plus or minus square root 7. Now we've got it set up here. If secant theta is equal, cosine theta is equal to that, then that means the x-coordinate in the unit circle is equal to that. We can break this up into 2 cases, one for the plus sign, one for the minus sign. So here's the vertical line of all points x equals 1 over 1 plus square root 7. There's 2 places that vertical line intersects the unit circle. Hence there's 2 terminal rays that can give you cosine equal this number. However, in the other case, x equals 2 over 1 minus square root 7. That's less than negative 1. The vertical line doesn't intersect the unit circle. It's left at negative 1 right here. So there's no solution. We can throw this one out. Now here, we want to find to 2 decimal places the solution, because what we have here, if we calculate this, we know one of the solutions to cosine theta equals 2 over 1 plus square root 7. I guess I wrote it over here. Is the inverse cosine. So inverse cosine 2 over 1 plus square root 7. What angle is it? Is it this one or is it this one? Well, remember the arc cosine always has to be between 0 and pi, so it must be this one. It's not around here or down here. So the arc cosine is this one, and then what's the other one? By symmetry, this angle has to be the same as this one, the arc cosine, which is about 0.99 if you run it in your calculator. So this is also 0.99. The angle we want between 0 and 2 pi, I should have put that up here, 0 less than equal to theta less than 2 pi, means we have to go 2 pi back up that angle. So 2 pi minus arc cosine 2 over 1 plus square root of 7, if you run that out in the calculator, is 5.29 to 2 decimal places, meaning round at the second position after the decimal point. Alright, well the rest of these we want to establish identities and simplify expressions that we see. These are things that we haven't done enough on, I think. Suppose I wanted to establish this identity, that cosine squared root 2 theta minus sine squared root 2 theta is cosine 4 theta. Look what that is. It's a quadruple angle identity. You can rewrite a cosine of a quadruple angle in terms of double angles. How can we prove that? Well, here's one hint on these establishing identities work both ends towards the middle. Start with the left side here and the right side here, and work both ways. The book recommends starting with the more complicated side, which would be this one in this case. However, you're not required to do that. A lot of books make that recommendation also, so that's one idea. But here's what you want to do first. I call these rules of thumb. These are not always the best way you can get. Any way you can prove it is good. But this tends to be tried and true, almost always works kind of stuff. The first thing you do is that if there's more than one angle, and there's 2 theta and 4 theta. If there's more than one angle that you're taking trig functions of, get one angle. So how can I get one angle if some of the trig functions have 2 theta and some of them have 4 theta? You use a double angle identity in this case. Rewrite cosine 4 theta as cosine twice 2 theta. Now it's double the angle 2 theta. By the double angle identity, cosine of 2 alpha, we can call this, is cosine squared alpha minus sine squared alpha, right? So this is cosine squared alpha is 2 theta minus sine squared 2 theta. Now I've got in terms of all one angle. Oh my goodness, I've already got it, right? All I had to do was put it in terms of one angle and I had it. So a lot of these established identities, if you just follow these rules of thumb, they work. This one was actually just one rule. Well, I'm going to jump to number 12 now. I'll come back to these because number 12 ties into what we just had a little bit. These rules of thumb that I gave you for proving identities also apply to simplifying expressions if you just leave out the work from both ends because you don't have both ends, right? You just have an expression. So 12a says to simplify this. 1 minus tangent squared over secant squared. How can I simplify that? Well, I first say, get one angle. There is only one angle, theta, so there's nothing to do. Now I say, apply algebra to eliminate compound quotients and combine sum quotients. Well, I could do that actually. I could write this as secant squared over secant squared and then subtract them, and that would work. That's actually a good way to do it too. I'm going to do it another way, although this is perfectly good to use this step here, right? This is secant squared over secant squared and combine them. Maybe you did that. Suppose I didn't recognize that. I could try a trig identity. I don't see a trig identity that makes it simpler, so I won't try that. The last hint is if you're stuck, try using sine and cosine only. I almost always do that when I see more than 2 trig functions. So if I have tangent squared over secant squared, I can write tangent squared as sine squared over cosine squared, and secant squared is 1 over cosine squared. Now if I finish these things, I go back to the top. I already have one angle. I can use algebra to get rid of compound quotients. Look, a quotient over a quotient. So I'll take top times bottom over middle times middle. There it is. To eliminate the compound quotient, get a single quotient. Now the cosine squareds cancel, and I've just got 1 minus sine squared. But wait a minute, that should look familiar, right? Now I apply a trig identity at the last step. Since sine squared plus cosine squared equals 1 by the Pythagorean identity, we recall solving for sine squared for cosine squared that 1 minus sine squared subtracting over is cosine squared, and we just write that for the last step. That's simplified. I already mentioned there's at least one other way to do it. Another way to do it is use the other Pythagorean Pythagorean identity and say that tangent squared is equal to secant squared minus 1. That would work also. So there's actually lots of ways to do this one. All I want you to do is get one way. So, but this is good rules of thumb right here. Let's try number 10 now, coming back. This one, when I say write it as a single trig function, this is the reason you want to, one of the reasons you want to memorize those trig identities is that this looks like one of them. Cosine, cosine plus sine, sine. Where have I seen that before? Right, I call it the looks like a duck rule, right? Waddles like a duck, it quacks like a duck. Must be a duck. All right, so what does that look like? I know cosine alpha, cosine beta, plus sine alpha, sine beta is the difference rule. Cosine alpha minus beta. So I call this alpha, I call this beta, alpha and beta. And remember, cosine, cosine plus sine, sine is cosine alpha minus beta. Plus with minus on the cosine identity, plus with plus on the sine identity. So I take alpha, 5x, minus beta, 3x, and I just have cosine of 2x. Easy as that. Here's number 11. Again, this is what does it look like kind of identity. I see square root 1 plus cosine over 2. That looks real familiar, right? Well, the hint is here. It's a half angle identity. How do I evaluate that? I said this looks like cosine 1 half alpha equals plus or minus square root 1 plus cosine alpha over 2. Since I have plus here, I want to use this one. Sine 1 half alpha would have a minus here. I have to use the cosine identity. So I use this, and I know that cosine 1 half alpha is plus or minus square root 1 plus cosine alpha over 2. It follows that the square root is plus or minus the cosine 1 half alpha. So I'll rewrite it like this with the plus or minus over here, and apply that identity. If I call this alpha, 5 pi over 12, right, is alpha, then I have to get cosine 1 half 5 pi over 12, right? So just replace alpha. Just use alpha equals 5 pi over 12 in this form of the identity. Well, is it plus or minus? Now, here's the trick. This radical sign means the non-negative number that has a square. So this is a positive number. If it's positive, now I have to think about, let's see, 5 pi over 12. Wait a minute, I want minus here, don't I? Plus or minus. Cosine of 1 half 5 pi over 12 is, let's leave it for now, just put plus or minus, is cosine of 5 pi over 24, top times top over bottom times bottom. Now 5 pi over 24, remember this is in the first quadrant, right? If this is pi over 2, that would be into the first quadrant. This is less than pi over 2, it should be 12 pi over 24. So we're somewhere in here in the first quadrant. This is positive. We want to get a square root. We want it to be a positive number because this radical sign means the positive number. So we choose plus here, and there's the answer, cosine 5 pi over 24. Well, I thought there weren't enough established identities on the practice exam, so I added one more here. Suppose I wanted to show that tangent x times cosine cubed minus cosine x is equal to minus the sine cubed of x. How can I show that? Remember the rules of thumb? Work both ends from the middle on an equation. Write this end over here, write this end down here, and then you just have to fill in the middle steps. You might follow the book's advice and start with the more complicated side. Well, I don't see an obvious trig identity or algebra to do, so I write everything in terms of sine and cosine. I write tangent as sine over cosine. Now I have sine over cosine times cosine cubed minus cosine. Now I can apply algebra though. Algebra says I can factor something out of here. This factors as cosine times cosine squared minus 1, right? This time this is cosine cubed, this time this is minus cosine. And now I observe I can cancel this cosine with this cosine, leaving sine times cosine squared minus 1. But wait, remember sine squared plus cosine squared equals 1. If you solve that, you find out that actually minus sine squared is equal to cosine squared minus 1. So this step is by the Pythagorean identity that sine squared plus cosine squared equals 1. If you subtract sine squared and add 1 to each side, subtract 1 from each side, let's see. cosine squared x equals 1 minus sine squared. That says cosine squared minus 1 equals minus sine squared. Then we apply that identity, replace this with minus sine squared. Now we've got minus sine cubed. We've established identity.